Hello, and welcome to episode number 11 of CS350 Online. I'm your host, Leslie, and in today's episode, instead of introducing a new topic of virtual memory, we're going to kind of polish off our discussion of processes, do a bit of review, by actually going over assignments A2a and A2b. So first, let's talk about the OS of the day. Now, this operating system is one which I'm going to assume the majority of you have never heard of, and yet it has played a very important role in where we are today in terms of operating system design and development. So this OS is called Alto Executive, and it was released in 1973. Now, when I say released, that's... if you're thinking it was some kind of major commercial release, I wouldn't really say that's accurate. This is a product of a place called Xerox PARC, and the machine that this operating system was released for is called the Xerox Alto. Now, what is Xerox PARC? You've maybe not have heard of this, which is always very surprising to me, but PARC is one of the most famous computing research institutions in the world. And you can thank the PARC Research Center for things like Ethernet and object-oriented programming and camel case, laser printers. There is the list of things that you can thank PARC for is never ending. Now, why is it called PARC? Is it like a green space? No, PARC actually stands for Palo Alto Research Center. So if at some point when all of this madness is over, you decide you would like to go Cali or bust, Xerox PARC does take interns. And I can tell you, if you were to have an internship with PARC on your CV, that would be a very impressive thing. PARC is pretty well known throughout the computing world as being one of the places. And so having that is, that's big. Also, Palo Alto, right? Palo Alto's pretty nice. Anyways, so just looking at the operating system here. So before we talk about the OS, the hardware itself. So I actually have a picture of it here on this screen. And no, the monitor in the picture is not on its side. That's actually the correct orientation. They believed that since people are working on paper, and paper is typically oriented in the portrait sense, that the monitor should be oriented portrait as well to mimic a sheet of paper. The computer itself, now for 1973, this is a really big deal. That computer there is no bigger than a small filing cabinet that would fit under your desk. So in a lot of ways, you could actually consider the Alto to be the first personal computer. Now, of course, the price tag on this particular machine would have put it out of range for the vast majority of individuals. It wasn't purchased by common folks. It was really mostly big businesses that might have purchased one for fun, but not many of them actually left the research facility themselves, is my understanding. Now, the machine had, in a lot of ways, it does look like a personal computer. You've got a standard keyboard, albeit one that probably weighs 20 pounds. You've got a 3-button mouse there, and that's actually really interesting because this is 1973, and if you look at all of the previous operating systems up until now, you've got command line driven, keyboard driven interfaces. This computer had a 3-button mouse, and it also had a 5-button chord keyboard, so you could actually play like music. But other than that, it's very much looks like just a very large desktop computer that you would have at home, on wheels, of course. So what about the operating system? So obviously we have a mouse. So there's going to be a pretty big difference between the operation of this OS and the OSs that came at the same time and preceded it. And that big difference, which is written in great big bold uppercase letters on the slide, of course, is that this operating system actually had a desktop with a mouse-controlled GUI, i.e. point and click. Now in 1973, in order to support having a real-time operated desktop GUI, they had to make a few concessions. For one, this whole thing we've been talking about keeping user code separated from kernel code and making sure that the CPU is in different modes so that while you're a user process, you can't access certain regions of memory and you can't execute certain instructions. Well, for the purposes of optimization, they actually did in this operating system permit user applications to access microcode. Because, as you can imagine, there was a lot of work that had to be done to create an interactive experience for the desktop environment. So they were going to do whatever they needed to do to make sure that actually worked. And I don't think at this point in time security really was a thought that many people had. And in fact, this is like the dawn of some of the earlier forms of internet. And people really weren't thinking about security back then because they were thinking of this idea of the internet as being a bunch of cool computer people who are just beyond thrilled to talk to each other. Why would they start attacking and stealing things? So security wasn't so much of a concern here. So, of course, this operating system did, of course, support Ethernet and LAN. And in fact, they actually had LAN parties with some of the video games that came with A2a, which was kind of neat. So at the bottom that I have here, so the operating system had all the other regular features you would expect, like preemption and so on. But at the bottom here, what I wanted to show you was what some of the icons on the desktop actually look like. Because if you look at these icons here, you'll recognize all of them. You've got an empty folder, an empty document. Now, a record file is something that we don't really use, but we've got a printer and a trash can. These icons, it doesn't matter if you are using a new Linux-based operating system. It doesn't matter if you're using Solaris or Windows or Apple products. These icons have kind of, even though, of course, they've been colorized and the number of pixels used to render them has gone up, the icons are still the same. So you can thank this lovely operating system for that. Now, just wanted to show you some screenshots of this OS itself. It's actually quite hard to dig up some screenshots or videos of some of these really old operating systems because I think at the time people didn't really see that as something as they needed or they wanted or they cared about. But I was able to find some for A2a. So what you've got here is you've got a system browser open where you can actually go through files using a point and click device. And it looks like they have some code open. This is actually a code window. And they've got two code windows. And just judging from the code I'm seeing in these two windows, it looks like they're working on some Smalltalk, which I believe is actually a product of Xerox PARC. Smalltalk being one of the first object-oriented languages. And then it looks like there may be some other exploration of code. And there's an image open, and there's a mailbox for email, and a clock, and a calendar. And also note that these windows are overlapping each other, and you can move them around. This is pretty cool. Yes, it's black and white. It's 1973. And they had things like paint programs, and they had pinball games, and they had all kinds of different fun things. One of the favorite test images in the paint program was this little piggy drawing with the little rainbows here. And I know, again, it's all dithered, but, you know, it's 1973. It's still really cool. Cute little piggies. And, oh, look, that little piggy has a little heart for his nose. That's kind of cute. All right. Now, another interesting thing about A2a is that this has actually been the inspiration for the design of many of the desktops that you actually use today. So it's rumored that Steve Jobs couldn't actually afford to purchase one of these machines because at the time, you were looking at spending over $10,000 just to buy one of these machines. But it is rumored that he actually went to Xerox PARC and actually spent some time working with the developers there, just learning how to use it, looking at the UI, and it's said that this is actually the inspiration for some of the design elements behind macOS. It's said. And the reason why I say it's said and not, this is not a definite thing, is because there are lots of stories in computing where we believe them to be true, but there's actually no definite proof. So for example, one such thing is there's a quote that people think Bill Gates has said about how no one will ever need more than 64K of memory. And I believe it is rumored that he said this in the 80s. So I actually went down that rabbit hole to try to get like an audio clip of this or to actually get like a script from whichever event he supposedly said this at. And the only thing I can say is that there's no definitive proof whether he said it. Is it believable? It's believable, but I cannot find any proof. So that's why I'm saying the story is and not a definite thing. All right, so this is our OS of the day. Now, before we get into just talking about things like A2a and A2b, I first off want to say I hope that you all had a good reading week, and I hope that you did manage to get some kind of rest or relaxation. I know it's during these online terms, it's really hard to create any kind of schedule or even know what the hell day it is, because you're not actually going somewhere on a daily basis. So you have no concept of, is today Monday or is today Friday? I have no idea. But I do hope that you managed to have some kind of break over reading week, and that your other courses haven't overwhelmed you with, hey, it's reading week, you should do a whole bunch of stuff for us. So hopefully it was good. The other thing I wanted to say is we've posted another quiz, and hopefully you'll have a chance to see that. It's about processes, and we'll start posting some of the remaining ones over the next week. If you haven't started on the quizzes yet, my recommendation to you is to get started as soon as possible, because even though the quizzes aren't technically due until the end of the term, like the end of classes, not the end of the term, you don't want to leave them all to the end, because what's going to happen is every course is going to have something due on that last day of classes, because we're not actually allowed to have non-final assessments due after the last day of classes. So everybody's going to have something due on that last day of classes. And if you've got 20,000 people all trying to use Learn at the same time, that doesn't work out well. So don't leave it to the last minute. Try to get them done as quickly as you can earlier in the term. And also because it'll give you some feedback earlier on in case you've misunderstood some concepts. The other thing I want to say is I kept promising that I would post the Meltdown Inspector papers, so I have done that now. So for anyone who's curious about what happened a few years back with how a user program was able to steal information from the wrong privilege mode, those two papers are posted. And I want to say, so my background is not security. I'm not one of these people who was big on hacking when I was younger. I'd rather create things than break into things. But, so even without like a hacking or a security background, the two papers that have been posted are actually really approachable. And if you're interested, I would recommend you read them. It's obviously not required content. It's just there in case you're curious as to exactly what those are. And I'm also going to, when I get a moment, post the Unix version 6 code. It's just a good example of another operating system's code to compare and contrast against OS 161, and it's actually smaller. It's only like 9,000 lines, so that's kind of fun. I just have to remember to post it now. All right, so then let's talk about A2a and A2b. So if you haven't read the actual assignments yet, no worries. I mean, it would be helpful, but we're not going to worry about that too much. So these slides, by the way, are already posted on Piazza. I guess it helps if we have them up here. These are posted to Piazza. They are in the extra sample problems thread. So once upon a time, A2a and A2b, as you can probably imagine, actually used to be a singular assignment called A2. And this split actually happened long before I started teaching this course. But my understanding of the reason why A2 is split into two separate assignments was because debugging wait, PID, and exit is actually quite a nightmare. It's not that it's conceptually difficult, it's that the probability you get a deadlock or you haven't protected a race condition properly is pretty high. And in fact, most errors I see on assignment A2A are problems between wait, PID, and exit, either deadlock or a race condition. And the problem was that students would get caught on those two, and they wouldn't even get these 4 system calls implemented, that they wouldn't even attempt the 5th system call, which is, of course, execv. So to give students a better chance at actually getting these system calls to work, the assignment was split into 2. So the first part, A2A, asks you to implement fork, wait PID, get PID, and exit. So just 4 system calls on the first part. And we're going to go through those. And then the second part, part B, A2B, asks you to implement just exec-v. Now, what's interesting is A2a is actually significantly more code and I want to say much harder to debug. A2b is actually relatively little code, like very, very small amount of code, but there's a tiny chunk of it which might actually be the hardest 15 lines of code you've ever written, because it's just weird. But we'll talk about that shortly. So 5 system calls that you're going to implement between A2a and A2b. Now, one of the things I want to say is if you don't have the locks and condition variables working properly, you are going to have a very hard time for assignment A2a and A2b and A3 because the code base actually relies on those things to work properly at this point. So let's then talk about these first 4 system calls. So remember fork. Fork creates a new process, which is a copy of the currently running one. Now, a copy means that it is a separate process. That process will have its own ID, but the contents of the address space, the contents of the stacks and heaps, is actually going to be the same. So it's not that they're sharing an address space. It's just up to the point of calling fork, they will have the same address space. Now, fork will return in both processes, and the reason why this happens is because the child process, which is created by fork, inherits by copying the address space of the parent's stack, which means it's as if the child has executed all of those functions even though it is brand new, which means that the child is going to return from fork just like the parent. Now, one of the big differences is the child process is going to return 0 from fork to indicate it is the child. And if you are the parent returning from fork, we will return the PID. And we'll talk about how to implement that today. All right. Now, then there was wait PID. Wait PID is the ability to have synchronization between processes. So maybe you've implemented some kind of MapReduce system where you've created a bunch of map processes, and you can't technically run any of the produce processes until all of the map processes have completed. So you need some way to force your process to wait for its children to actually terminate, and that's what wait PID is going to let you do. It's going to let you wait for the specified process to terminate. And you are going to block when you are waiting here. Now, the one requirement, of course, is that the process you are waiting on must be your direct child. So it cannot be a parent, a sibling, a cousin, or a grandchild. It has to be your child exactly. Get PID is kind of a simple one. This should take you 1 minute to implement. It returns the PID of the current process. And then we have exit, which is going to terminate the calling process. But instead of fully deleting things from the system, we're only going to fully delete the process if there is another process alive that cares about you. So for example, if you have no parents, then when you die, there's nobody there to care about you as a process, because with processes, the only relationship that matters is the parent-child. So siblings don't care about each other, children don't care about their grandparents, or children don't care about their grandchildren, and so on. So with exit, you will fully delete a process if your parents are dead. But if your parent is alive, then we're going to leave behind some information about why you terminated, just in case the parent calls wait PID on you. And we'll talk more about that in a bit. So that's a review of all of the different system calls for A2a. All right. So we're going to go over A2a's implementation in a little bit more detail. And we're going to start by doing this in English. So first off, as you can imagine, if you are creating a new process inside of the kernel's implementation of this, you're actually going to need to create a new process structure. Because remember, a process is actually a structure. So once you've created the new process structure, then you actually have to create a new address space. Because if you actually look at proc create, it doesn't actually create the address space. And the reason for that is at the point where you're creating the process, you don't actually know in that instant how big the address space needs to be. So we can't, or we have chosen at least, not to create the address space in the process creation code. So we create the process, and then we're going to create an address space. And once we've created the address space, we're going to copy the contents of the parent's address space to the new address space that we just created. And then we'll attach that newly created and populated address space to the child process structure that we've created. So at this point, we have a child process, and that process has an address space which has been populated. Okay. We're making some progress here. Now, one of the things that we haven't done, and it's not done in this code, is we still have not assigned a PID number. Now, it's very common for people to want to assign a PID number in process creation. Most people do that. I'm not saying you have to. But so you're going to need to create a PID at some point for the child process, and whether you do that in proc create or whether you do it after you realize that you actually can create this process and populate its address space, that's entirely up to you. But regardless, you have to create a PID. That is not currently a part of the system. So what we're going to do is whatever you want. Some of the rules of creating a process PID number is that it has to be a positive integer and it cannot be 0. We actually recommend that you keep your PIDs to be greater than 1. But they certainly can't be 0. Now, why can't it be 0? Because if 0 was a PID and fork returns 0 to the child, then how would you know that this is the child process and not the parent if 0 was a valid PID? Now, you might be like, well, maybe we'll just have negative numbers. But we use negative numbers to actually be error codes. So PIDs have to be positive and they have to be greater than 0. Have to be. Now, what are you going to do to create this? If you read through these notes, you may notice it says, oh, you need to create reusable PIDs such that when processes are terminated, you can actually reuse that PID. We don't check that. We're not going to check that ever. We're not going to go through your code to make sure your PIDs are reusable. To be honest, there is no code that we have that could actually test whether you're reusing PIDs. So you do not have to create reusable PIDs. If you did want to create reusable PIDs, then what you would need to do is keep track of all the PIDs that are currently in use and then find some mechanism to, when you're creating a new PID, make sure it doesn't belong to something that already exists. That could be a pain in the butt to do. Another way to create reusable PIDs is to actually use the address of the process structure. It's a fun one. However, I want to warn you if you do decide to do that, because our PIDs are integers and addresses are unsigned integers. And so you can end up with some negative PIDs, and that's also very bad. That's actually quite simply fixed by doing some shifting to get rid of the negative, but I'm going to leave that up to you. The simplest, however, way, of course, of assigning a PID is to have a magical counter in the system. And that counter, every time you create a process, increments. And you might be thinking, well, I'm going to run out of PIDs at some point. What if the TA creates 2 billion processes? Do you honestly think any of us have time for that? If we have time to create 30 processes, that's a miracle. So you don't need to support 2 billion separate processes. If you can support like 64 processes or 100 processes, we're good. Number one, because OS 161 can't really support more than that. But number two, because the tests, we don't have them and we're not going to create them anytime soon. So, that's what we have for processes, PIDs. Sorry, I can hear my kids causing trouble in the basement. All right, now, however you assign the PID, one of the things that I want to warn you against is that if you're doing some kind of global PID structure, or if you're doing some kind of global PID counter, which I really do recommend the PID counter, that is a global shared object, which means that there could be multiple forks going on at the same time which means that multiple people could be trying to get a new PID at the same time. So make sure that you are having some mutual exclusion on a PID counter or your PID structure, whatever you decide to do. Put some synchronization around it. Now, if you're wondering, where am I going to create these locks or spin locks or binary semaphores that I'm going to use to protect my global PID counter? Where am I going to allocate them? Where am I going to create them? Because they need to exist before the first process exists. And the answer is you want to look for something called proc bootstrap. So if you look in proc bootstrap, any kind of creation for global structures related to processes, you should be creating inside of proc bootstrap. My recommendation is to create it at the very bottom of proc bootstrap. If you try to create a lock higher up in proc bootstrap, you probably won't have a good time, but if you do it at the bottom, you should be okay. Okay, so PID, do it however you want, but make sure you have synchronization if you have any global structures. The next thing to think about is now that you actually have the child process, you need to establish that parent-child relationship. And again, we leave this completely up to you as to how to implement it. A few hints that I could provide for you are that you only have one parent. So you could have either the PID of your parent and then have some global process table where you look up the PID to get the pointer to your parent process. Or if you wanted to just have a pointer to your parent process, both solutions work very well. And then for your children, you can, of course, have as many children as you want. So you are going to want to have either an array of PIDs or an array of pointers to your children. Again, do whatever you want. But my recommendation is to not go out and create your own linked list structure because OS 161 already has a dynamic array. And I recommend that you actually use the dynamic array that's already provided by OS 161 because it is tested and it actually works. If you need to learn about how the array works, if you go into kern test array.c, you can actually see an example of how the array structure is actually being used. Again, you can do this however you want. We don't care. And if you're sitting there, but it's going to have O of n time or O of n squared time, yeah, we don't care. This is not a course about can you make the world's most efficient operating system. This is a course about giving you some experience with some lower level code. We care more that you got it working than how efficient it was. So keep that in mind. So after you've got this process created, it's got a PID, it's got an address space, and the parent-child relationship has been established, you might be thinking that you're done, but you're not. Because when you create a new process, you don't get a thread. And remember, it's not so much the processes that execute, it's the threads that execute instructions. Because a thread is a sequence of instructions, and we have not given our new process a thread. So we need to give this new process a thread. And then so we create this new thread. Now the new thread, remember every thread has two stacks. Our new thread has a user stack. We got it from the parent when we copied the parent's address space into our new address space. But what the new thread doesn't have is a kernel stack that's sufficiently populated such that we could return from kernel mode to user mode and go back to executing from the point of fork. So what do we need to do? We are going to need to take the trap frame, which will have the pointers to where in the user stack we actually are and all of the values that will allow us to return to user space from the parent, and we need to put it onto the child process's kernel stack. We'll talk a bit more about how to do that in a moment. But once you have put that trap frame onto the child's thread, then we're going to call this magical function called MIPS user mode, which is, the analogy I use is it's returning from a fake exception. The exception wasn't raised in the child process, so if we need to return from kernel land back to user land, we almost need to return from a fake exception, and that's kind of what MIPS user mode is going to do. Now, this might seem like a lot of code that you have to implement by scratch, but it actually isn't. because a lot of this is already implemented for you. So for one, the process structure already exists, but you are going to need to add fields to it. For example, the PID and anything to do with the parent-child relationship and any of the extra synchronization things you might need to implement wait PID. So you're going to have to make some modifications to the structure. You'll find the proc structure in kern include proc.h. Please do not remove anything, but you are welcome to add whatever you like. The next thing is you don't actually need to manually malloc the memory for the process structure because there's a function that already does that, and that's called proc create run program. And you call that and it gives you a new structure or a new process structure. So that's pretty cool. The only thing you need to watch out for is it's possible for proc create run program to fail because maybe there's not enough memory to actually create the new process. So you need to check for errors from proc create run program, and if you get an error, you need to not k-assert and panic because k-assertions actually cause panics. What you actually need to do is you need to return the appropriate error code from sysfork so that the user program can be told that, hey, your fork didn't succeed. If my fork doesn't succeed as a user program, my operating system shouldn't blue screen of death. So you should not be panicking inside of these system call implementations. That would be really bad. So all you've got to do is create a pointer and then call proc create run program and check to make sure that the result isn't null. Now, to create the address space, you may be like, okay, well, I've got to measure and see how big the address space of the parent is, and then I got to use memcopy. Nope. Actually, this is also all handled for you. So you're going to create a pointer, and you're not going to allocate any memory because ASCopy is going to do everything for you. ASCopy is not only going to create a brand new address space for you with the correct size, it's also going to copy the contents of the old address space into the new one. So you create a pointer and you call ASCopy. And then you can attach that brand new address space to the process you just created. Now, some people do this in the single step with ASCopy. Some people actually separate ASCopy from assigning the address space. That's up to you. But do be careful because there can be synchronization issues here, and while you are setting the address space of a process, you should probably have a lock on that process so no other changes can happen to it. And so my recommendation to you is to look at the function curprocsetAS to see how we synchronize that with a different function. Now, do not yourself call curprocsetAS because we are not setting the parent's address space, and that's what that function would do. We want to set the child's address space. It's just that that code will show you a safe way of doing that. Again, ASCopy may return an error, for example, if there's not enough memory, and so you need to be able to handle that. Okay. Hey, that's pretty neat. That's like 4 lines of code, and I've got fork mostly implemented, right? So now you need to assign the PID. And again, a lot of people will actually assign the PID inside proc create run program or proc create. That's entirely up to you. I don't care. Just make it work. The PID has to be greater than 0. And other than that, we don't care. Genuinely don't care. Create a PID. For the parent-child relationship, it's, again, completely up to you how you implement this. If you are creating any structures, you should be doing the allocation of those structures inside of proc create. So just keep that in mind. And again, your PIDs, by the way, do not have to be reusable. So if you have an old version of these notes, don't worry. For the person on Twitch, these slides are actually found in the extra sample problems post that is pinned on Piazza. So you have access to these. And you've had access to them the whole time. All right, so actually creating and setting the address space of our new process is very simple. But now we actually need to create a new thread. The only way that we can really create a new thread is by calling thread fork. But as you know, thread fork actually takes 5 arguments. The first argument is the name of the thread. We don't really care about what the name of the thread is because that's kind of for debugging purposes only. The second parameter of thread fork is the process we want this thread to belong to. So because we want to create a new thread for the child process, what we're going to do is we are going to pass the address of the child process in as our second argument to thread fork so that the new thread gets attached to the child. And then what we're going to do is, well, wait a minute. We have to pass a function that our child process's thread is going to execute. What is that function? Is it an empty function? And the answer is no, it's not an empty function, but it is something you're going to need to do. The purpose of the function in our thread fork is going to be setting the kernel stack up for this brand new thread. Because remember, when you create this new thread, its kernel stack is empty. So it doesn't know how to return from kernel mode to the user stack that's already populated by ASCopy. So we need to set up the kernel stack for our brand new thread so that it can return from the fake exception and actually go back to user mode. So this is what we're going to do for our function in the thread fork operation. And there is a signature there already called enter forked process. We recommend you edit the signature, but you can create your own function if you want. Don't really care. Just make sure the signature matches to what thread fork is expecting, as you see here. And enter forked process, you should be passing the trap frame of the parent. And then in enter forked process, we want to take the parent's trap frame and put it onto the stack. Now that might seem very complicated, but it's not. So we have a little bit of code here, but I'm going to actually just bring it up in OneNote. So what you've got to do is, so you've got this, uh-oh, my tablet fell asleep again. Wake up, tablet. Wake up. My tablet fell asleep. That's annoying. Doesn't want to wake back up. Well, let's just use a VI window instead. That's just as good, right? Let's write some code. So what you've got is this enter forked, I can spell really, process. And it's going to take some args, and one of those args should be a trap frame pointer. What you need to do in enter fork process is you need to take that trap frame and you need to put it onto the stack. Now you know that this trap frame, it's coming into you from the heap. So how do you put something onto the stack? Well, ask yourself, what kinds of variables are on the stack? Local variables. So what we want to do is make a local variable that contains this trap frame. So it's actually quite easy. Like so. Now, there's some casting that you're going to need to do here because this is not a valid signature for enter fork process. This actually has to be a void pointer. So you're going to have to do some clever casting down here. And if you're worried about things like, but this is a shallow copy, that's totally fine because the trap frame is just a copy of all the registers. A shallow copy is more than sufficient. So I've made a local variable. I have actually copied the contents of the heap one into my local one. And then I need to do some more work. We're not quite done. Remember that the return value for fork from the child is different from the return value for fork from the parent. The parent is going to return through syscall and get its return value set up that way. But the child thread isn't going to do that. So we're going to need to set up the return values from fork here for the child process. And you can do that by simply saying, and I'm going to let you look up the exact names of this, v0 equals whatever, and then you'll have TF, A3, and then don't forget to increment your program counter, which is EPC, by, of course, 4. So there you go. You've set up the return values because remember, the child isn't going to return through syscall. So we have to manually set this stuff up here. And then now we can call MIPS user mode. Okay. However, we're not quite there yet. One of the problems is that if you take the parent's trap frame and you pass it through here, it is entirely possible that the parent returns from the call to fork before enter forked process for the child ever runs, which means that the trap frame pointer that you just passed in, well, it was a pointer to an address on the kernel stack of the parent's thread. And because it's returned from kernel mode, that trap frame disappeared, which means you are now copying garbage onto the stack of the user process. So we don't want to do that. So there's 2 solutions that you can go for here. Solution A, which I don't recommend, is to add some synchronization. So force the parent to block until enter forked process in the child has executed. I don't recommend that because it's going to be slow. And every one I have seen tried to implement it that way ended up with a deadlock problem. I don't recommend it. Not to say you can't get it working. I'm just saying, in my experience, it's both slow and rife with problems. The easiest way to do this is to simply make a copy of the parent's trap frame in a place where it can't get destroyed from the parent returning from fork. And all you have to do is, before you call thread fork, make a copy of the parent's trap frame on the kernel's heap. So using kmalloc. And then pass a pointer to the copy that's on the heap into enter fork process. And then after you've put that copy onto the stack, then all you need to do is free it. And do make sure that you free it if you choose this method. So that method is faster. Yes, it uses a little bit of memory, but it's like 32 integers. Who really cares, right? All right. So now you actually have a new process with an address space, a PID, a parent-child relationship, and a thread. And that thread has a stack that will permit it to return from fork, which means you're actually done fork now. It's not so bad, right? It's really not that bad. And by the way, all of that stuff you can find here. All right. The next one I want to talk about is wait PID, and we're going to talk about this at the same time as exit because these two really do work together in a lot of ways, at least their implementations do. So wait PID lets us block until our child process has terminated. So the idea is if you call wait PID on a PID that is not your child, wait PID will return an error code that says this is not my child. If you call wait PID on a process that doesn't exist, wait PID is going to return an error code that says this process doesn't even exist. If you call wait PID on a process that is your child, there are 2 possibilities. The first possibility is your child has already terminated, at which point you don't block, but you are going to grab the exit status and exit code from your child. Think of it as the message, the inheritance it left behind when it died. You're going to grab that information and you can use that to determine why did the child die and did it leave me a message behind. If, however, you call wait PID on your child and your child is still alive, then the calling process is going to block. And then when the child process terminates, the blocked process should wake back up, grab the exit status and exit code, and return from wait PID. So this gives us the ability to wait, which means that you can see why exit is involved, because exit is giving us the exit code and the exit status. So I've already said you can only call wait PID on your children. So one of the first things that you're going to need to do in your implementation of wait PID is check to make sure that the PID that's passed through is actually one of your children. And what's going to happen is when a process calls exit, and I'm going to jump ahead here to exit. When we call exit, what needs to happen is you need to check, do I have a living parent? If I have a living parent, then they might care if I die. So therefore, when I call exit, I'm going to leave behind an exit code and an exit status. And the exit status might be something like, hey, I called exit. So I'm terminating because I called exit. And the exit code will be the argument that you have passed through exit, because exit takes a parameter. So if your parent is alive, not a zombie, but actually alive, you are going to keep the exit code and the exit status message for that child process. And if that parent is sleeping, waiting on you to terminate, then you should also wake them up. If, however, you call exit and you have no living parent, you can just fully delete yourself, because only your parent can call wait PID on you, which means only your parent cares about your exit status and exit code. And if your parent is dead or doesn't exist or isn't alive, they can never call wait PID on you, so we don't need that information. Now, when you call exit and your parent is technically alive still, you're going to enter a state called the zombie state. You have no executable code anymore. Your thread is gone, but the process still kind of exists in this weird non-runnable state. So you still have a presence, you still have a PID, you still have a parent-child relationship, you've got this exit code and exit status lying around, but you don't have any runnable threads, and you don't even need an address space anymore. We call that a zombie. So keep that in mind. Okay, so exit is going to produce for us this exit code and exit status that we're going to use back in wait PID. So if you call wait PID and the process is your child and they have already terminated, that is, they are a zombie, then you're going to grab the exit, grab the code and the status message that was left behind. You are going to process them using a macro I'll show you in a minute, fully delete everything that belonged to that child, because if you've conducted the autopsy once, we don't need to conduct the autopsy again. That's just creepy and weird. So you can only call wait PID on a process once. So we're going to get its exit code and exit status, return that from wait PID while we are fully deleting the rest of that zombie child. If, however, we find our child is alive still, then we need to cause the parent to block. Now, there are lots of opportunities that you have to implement blocks. I'm going to give you a big recommendation right now. Use a lock and a condition variable, and each process should have its own lock and its own CV. And since you are waiting on your child to terminate, you should wait on your child's CV. It's not to say it can't be done any other way. It's just that's the easiest path to success. I've seen people do it with semaphores. I've seen people do it with a global waiting pool. I don't recommend that. That's really slow, but it does technically work. Your choice. Okay, so there's wait PID and exit kind of together. Now I said you're going to take the exit code and the exit status message. So the exit status is how did you terminate? So I terminated because I called exited, or I terminated because somebody called kill on me. And then the exit code is what was passed from exit. And wait PID is going to return these two values as a singular integer. And to turn it into a single integer, you're going to use this macro mkWaitExit. Now you'll note that mkWaitExit takes only a single argument. It's because it is assuming if you're calling mkWaitExit, then your exit status is wExited. And so it just takes the exit code and combines it automatically with wExited. And that is the value you're going to pass back through wait PID. And you'll notice in the code there's already a basic implementation of wait PID, and the code to actually pass this back is already there, and you just need to make a teeny modification to it. Well, you need to make a few modifications to wait PID. Okay, get PID is not really worth talking about because you return the PID of yourself. We don't need to talk about that, right? It's 1, 2, or 3 lines of code, like including like the functions and the brackets and the comments. It's like nothing. Now, one thing I want to warn you about is with wait PID and exit and fork. The most common problem I see is synchronization issues revolving around the fact that when the parent calls wait PID, you're going to go through your list of children to check, is this one of my children? And if it is one of my children, then you're going to check, is my child alive or dead? And when you are checking whether the child is alive or dead, you have to understand that the child may be changing that status at the time you are looking. Context switches, remember, they can happen anywhere. So it's not safe for you, the parent, to check the child's whether they're alive or dead without synchronization. So you need to make sure that if you are accessing any field inside of any process, you own the mutex for that process. So if I want to check whether my child is a zombie or not, I need to, at least in the keep the process around without an address space implementation, you need to actually acquire the lock for that process to make sure that you are not doing bad race condition things. And this includes yourself. So if you are the parent and you are accessing your array of children, well, maybe you should probably also own your lock when you do that. So the synchronization for this is tricky. Be very careful. This is where most of the bugs for this assignment come from. And again, the hints I've given you here are actually quite specific to a given implementation, but the general idea of if you're accessing a process's fields, you should own that process's lock, that holds. If you have a global process structure or a global array of all the exit and wait codes that were left behind, then you still need a lock to protect that, because the structure could be changing in real time. So synchronization is really important here. So that's A2a in a nutshell. These slides, of course, are posted to Piazza already. If you have an older version of these slides, which does actually exist, one of the things I want to warn you about is that there are lots of other versions of wait PID which use different flags to do things like wait for the first child to terminate, or instead of blocking, return each child to indicate that the child has not terminated. Those are things you could technically implement if you wanted, but we're not going to test them. Furthermore, why would you do it? We will never know that you've done it. And even if you did, we don't have time and we don't give out bonus marks for this kind of stuff. So it's just not worth your time. Do the basic implementation and move on. All right. So now I want to talk about A2b. Now, I'm going to talk about how these assignments are graded at the very end, because it's really important you know. But A2b relies on A2a working. Okay, it does. If you don't have A2a working, you won't get full marks on A2b. So in A2b, you are only really responsible for implementing execv, which is changing the program that a given process is running. So the process structure is going to stay the same, like you have the same PID, the same parent-child relationship, but the address space is going to change. And as part of that, you're going to need to be able to accept command line arguments for those programs. And you're also going to modify run program, which runs the first user process from the command line in the OS. You're going to need to modify it so it also accepts arguments for its programs. So remember, execv is changing the program an existing process is running. And if you actually look, there is a function that already exists in the OS that is very similar to execv. It's called run program. which you're going to need to make some modifications to already. So run program is going to load and execute the first program, user program from the kernel menu. So it opens the program file, it creates an address space, and then it is going to set the current process's address space to be the new one it just created. And then it's going to load the address space, because creating and loading the address space are two different things. One actually creates the address space structure. The other one is going to populate it. And then after it's loaded the address space, we're going to create our user stack, because our user stack isn't specified in the binary file. So we're going to have to do that ourselves. And then we're going to say, go forth, process, and execute. Run program, this is what it does. And this code already exists. And this code should be the basis for your exec-v. So my recommendation is when you're implementing sysexec-v, open up run program, copy the contents of run program, and paste them into exec-v. There's your basic implementation. Now you're going to need to make some modifications, but not a lot. You're allowed to copy code from other parts of the OS. Now here in green, by the way, you'll see the names of all of the functions that we use, of course, to do all of these different tasks. So here's the difference between exec-v and run program. So in light gray here, these are the things that should remain identical. So we're still going to need to open the program file using VFS open. We still need to create a new address space, set the process's address space, and clear the TLB. Now you might be wondering, what is this TLB thing? I haven't heard of this yet. We're going to be talking about that in the coming days, so don't worry too much about that. But essentially it's a cache, and our cache will have old values that are invalid, and because we are changing the program, those cache values are no longer useful, so we need to clear them out. So we'll clear the TLB here. And loading the program into the address space, again, those three things remain the same. Now, what's different with exec-v? Well, exec-v doesn't have the name of the program already in the kernel. The name of the program, along with all of the arguments for that program, are actually stored in the address space of the process that was running. So we need to copy the arguments and the program name from the address space of the existing process into the kernel. Now, why can't you just copy them from the old address space into the new address space? This is going to make more sense as we talk about virtual memory, but the problem is the old address space and the new address space actually use the same addresses. So how do you know that you're copying from one to the other? It's not easy. I'm not saying it can't be done, it's just it's not easy. The other thing is that we're actually going to be destroying the old address space. So on Twitch here we have, isn't the TLB some CS351 thing that we all forgot about after the course? Yes, it is. But don't worry, we are going to talk about it lots more. And if you've forgotten about it, well, I mean, that's life, right? The second you're done an exam, you forget the course. Okay. So what we need to do is we need to first copy the program path from the user's address space into the kernel. And then we need to copy the arguments. But before we can copy the program arguments, we actually need to count them because we don't know how many there are. So the arguments, as you see, are actually stored as a null terminated array of pointers to strings. So you're going to have a bunch of string pointers, and the very last one will be null. So you're going to count the pointers that are not null. When you get the first null, there's no more args. You know how many arguments you have. And then you're going to go back through and you're going to copy each of those individual strings from that address space into the kernel. That's a tricky part. The argument stuff, I'm going to tell you, leave it till the very end. You do have to copy the program name in, though, because you need to pass it into VFS Open. So then you go about your business with creating the address space, exactly the stuff we copied over from run program. But then after we've loaded the address space with load elf, what we need to do is we need to create the user stack. Now, before we had AS defined stack and it just created an empty stack for the user program. But now But now what we're doing is we need to actually push the arguments for the new program onto the stack. So our recommendation is to actually create your own version of as-defined stack that both creates the user stack and populates it with the user arguments. And this will make more sense in a minute. Now on Twitch, there's a question, why can't we just copy until we hit null? I mean, you can do that, but here's the thing, and this is the number one mistake I see on this assignment, A2b, is people copy things from the user space into the kernel, but forget to actually allocate memory or enough memory for those strings in the kernel. So if you count the number of arguments first, then you can more easily allocate how much memory you need to store those arguments in the kernel. Otherwise, you're going to have to be allocating memory as you go, which it's doable. It's just, I see a lot of mistakes. I don't care how you do it. I really don't. Just make it work. Okay, so you're going to need to create your own version of as-defined stack, and that's going to both create the stack and push the arguments onto it. Once you've created the stack, it is safe to delete the old address space. And then we're going to call enter new process with slightly different arguments than run program. So again, this is still very similar to run program. Now, I want to talk to you in greater detail about this argument copying. So first off, it is entirely possible to get through this assignment without using copy in. But you shouldn't. You shouldn't. So when you want to transfer memory between a user address space in the kernel, you could just directly use the addresses. And you could just directly do a mem copy or whatever you want to do. But it's not safe because you are making the assumption that the address that the user program has given you to copy from is actually valid. And if you try in the kernel to copy from an invalid user address, then the kernel is going to crash, not the user program. And I don't want my user programming being stupid to cause my OS to blue screen of death and die. Kernel panic. So we have these special functions which are going to validate the user addresses before we actually use them. And they are called copy in and copy out. You should always use these when you are dealing with things in the user address space, whether it's copying from user to kernel or kernel back to user. You should use these safe copy functions to go between those two different regions of memory. So, and by the way, this is not something that's unique to OS 161. You will find things like copy in and copy in stir and copy out. You will find those even in the Linux kernel itself. So these are actually very common functions across operating system implementations. So what we want to do is when we are copying in the name of the program, since the name of the program we want to run is a string, we're going to use copy in stir. Copy in stir is used to copy a null terminated string from the user address space into the kernel. Make sure before you do this, of course, that you actually allocate some space in the kernel for that string to live. And then for any kind of fixed size variable like an integer or an array that you know has 10 spaces in it, you'll use copy in and you'll specify how many bytes to copy. And again, always make sure you're allocating space in the kernel before you copy into it. That's like the number one mistake I see in this assignment. And then copy out and copy out stir. Copy out stir is for copying a string from the kernel back into the user address space, and copy out for fixed size things. So my recommendation for you is to first implement execv by copying run program into execv and only copying the program name in. When you have execv working with just the program name, only then should you move on to the arguments part, because the arguments part is tricky. Now, copying the arguments from the user land into the kernel, that's not so bad. What you need to do is you copy in each of the pointers to strings and check to see if they're null to count how many arguments there are. And then after you've copied in each of the char pointers, then you want to allocate the space for the argument strings, and then you're going to copy in individually each argument string. And you can make assumptions that the program name is less than 128 bytes and each argument is less than 128 bytes. That's fine. There's no TA that's going to sit there and mash their keyboard for an hour. None. Ooh, looks like I'm getting a delivery. Woohoo! I apologize. There's a chance my doorbell is going to ring here in a moment. All right. So, when you're doing the arguments part, you should kind of do it in a few different phases. As I said, I expected my doorbell to ring. The first phase, you've got exec_v working with no arguments. Okay. When you have exec_v working with no argument passing, move on to argument passing. Phase 2, count how many arguments there are. Using kprintf in the kernel, print out the number of arguments you found. Make sure that the number of arguments you found in the kernel is the number of arguments you expected. If it matches, then move on to actually copying the argument strings into the kernel. Once you have the code for copying the argument strings, you need to validate that it worked. You validate it worked by printing using kprintf all of the arguments you copied in out from the kernel. Once you have validated you have the correct number and the kernel now has the correct arguments in the kernel, only then should you attempt the very last phase. The very last phase is putting the arguments onto the stack of the thread. And this is the trickiest part of this assignment by a long shot. This is requiring what's called byte alignment. So when you are implementing a compiler, and when you actually compile code, the arguments for running a program are expected to live on the stack in certain locations so that the program actually knows how to find all of its arguments. And this is true in OS 161, this is true in New Linux, this is true in Windows, this is true in macOS, this is true pretty much universally. The arguments to a program have to live on the stack at certain positions. And it's true even in a greater sense. You might have heard of something called byte packing for structures. So how a structure is laid out in memory is really dependent on the compiler and the operating system. And I've actually come, and it's even dependent on the program. If you have things packed in the wrong way, then the other program won't be able to read them. And I encountered this bug with working with Unreal Engine 3 back in 2010. I was trying to have motion capture data passed as a structure in real time from the mocap system into Unreal to drive the virtual characters. But it didn't work. So I had the structure and I was getting the data, but it was garbage and I could not figure out why. And it took me a month. Why does my X coordinate have half of the Y coordinates data in it? And as it turned out, it was because the mocap data output the structure with the standard Windows structure alignment, but Unreal Engine only accepted structures with 4-byte packing, which is not how structures were aligned in Windows by default. And so I had to write an intermediary program to repack the structures between the mocap system and Unreal. And we're going to have to do something similar here. We need to align our arguments for the user program that we're about to run on the stack in a very specific way. And this is the specific way you need to do it. So, first off, there is a typo in this. It is not ints and pointers must be 4-byte aligned. It is pointers to strings are 4-byte aligned, and I need to edit this. So ints, integers, and pointers to integers need to be 8-byte aligned. Chars can be 1-byte aligned, which means they can be anywhere. And char pointers need to be 4-byte aligned. And everything else has to be 8-byte aligned. Now, what does this even mean? Alignment means the address has to be divisible by that number. So if we say something has to be 4-byte aligned, then the address has to be divisible by 4. If we say that something has to be 8-byte aligned, then its address has to be divisible by 8. And there are very handy macros in OS 161 to help you round up things. So what you're going to do to align things on your stack is first you're going to push the strings onto the stack. So the strings are going to actually be at the highest stack addresses. No alignment is required here, but do make sure that your strings are null terminated. After you have pushed all of the strings on, record the address of the first character of each of those strings that you just pushed onto the stack. And then what you're going to do is above the strings, you're going to push the addresses of all those strings onto the stack. Those addresses have to be at addresses divisible by 4. And the very last one needs to be null because that's your array of pointers. And then at last you'll push the final bit. Now I want to show this to you so you can actually see what it looks like. So here is an example stack. So as you can see, we have actually pushed these arguments. There are 2 arguments, -L and Mr. Goose. So I have Mr. Goose here at the bottom, and you'll notice there's some extra space here. That's okay. Extra padding should just be set to 0, and that's totally fine. Extra padding, zeros, put it wherever you need to do to make this work. So I've got Mr. Goose here. And then above it, I have the other string, which is -L. And then I also have the program name, which is also considered an argument. So we've got all 3 our arguments here. And now, above this, I'm going to have all of my pointers to these strings. So there may need to be some space between these 2 if these wouldn't live at addresses divisible by 4. So each of my pointers is going to live at an address divisible by 4, and there's the null to indicate the end of the array. Now, the pointer to the array, so the address of this array of string pointers has to be at an address divisible by 8. So please do, my recommendation is to calculate that address divisible by 8, and then since the pointers are already 4 bytes apiece, just plop them all down after that, and then you don't have to do rounding up with each individual one. So why can't you just copy until you hit null? I mean, you can. There's lots of different ways that you can do this. So if you have determined what the aligned first index of the array needs to be, then you can just write to it and just keep writing until you hit null. But again, it depends on how you've stored those pointers in the kernel and so on and so forth. Now, a couple things to note. When you are writing to the stack, make sure that you don't call kmalloc. The memory has already been allocated. All you need to do is calculate the address and write. So no mallocing here for putting the arguments on the stack. Calculate the address, write to it. I like to go backwards, so I keep a current top and then I just move it up as I add things. The other thing, you're going to be using copy out. Make sure that the addresses that you are pushing onto the stack are actually user addresses, and we'll talk more about that in the coming days. What a user address is, make sure they're not kernel addresses. Okay, so the last thing that we have, so here's just some hints. Again, all of the steps that I've given you, they're written down here in case you want to read about them again. And then I want to talk about grading, but instead of talking about grading here, to finish off this episode, what I want to do is I want to go over to a terminal, not a terminal, you know, a web browser. And I want to actually show you the assignments. So A2a marking report. This assignment is out of 30, A2a. There are only 4 tests. They are 1 fork, PID check, wide fork, and fork test. Those are the only 4. You have the source code to all 4 of these tests, so we will not answer on Piazza whether your output is correct or not, because you can open up the code and you can read it and figure it out. That's a long-standing tradition because you have all of our test code. There are no secret tests. We will be running these tests on 1 core, but we will also be running them on multiple cores as well. Now, if you fail these tests, we have code inspection as a mercy. And essentially what happens is if you score less than 14 out of 30 on the tests, we will inspect your code to see how far you got, and we will give you some mark up to 14, and that will be your grade. So you'll still fail the assignment, but you would get not 0, assuming you actually tried. You would get some marks. So those are the 4 tests for A2a. Now, A2b is a quirky one. So on A2b, is out of 50, and we're actually going to completely retest A2a. So if you didn't get A2a working, you need to keep working on it for A2b. And then after we retest the 4 tests from A2a, we're going to do the A2b tests. The A2b tests are Hog Party, Sty, Arg Test, Tests, and Add. Some of these do not have command line arguments. I believe it's Hog Party and Sty do not have command line arguments, but the other 3 I believe do. So, and these also make use of fork, wait, PID, and exit. So it's really, really important for A2b that you actually get those 4 tests working. If, again, you fail the A2b test marks, so you get less than 16 out of 32, we, again, have this code inspection to give you marks. But there will be on A2b no code inspection of A2a because we assume that you've made progress there. So those are all of the tests. Again, you have all of the code for this, so we won't give any hints with respect to that. All right, so that's all there is for implementing A2a and A2b. And if you're confused about this user kernel addresses and address spaces between the 2 and TLBs, don't worry, we're going to be covering those topics in the next couple days, long before you need them for A2b. So we will see you all on Thursday, where we will start, finally, virtual memory.
To succeed in today's ever-changing business arena, Canterbury Clock Company realized it had to switch gears, move forward. Microsoft was there to help, thanks to Joe. He called Microsoft toll-free and asked for the switches on, a free video just for Lotus 123 and WordPerfect users. The timing couldn't have been better. He watched how upgrading his software to Microsoft Excel and Word for Windows could save his department lots of time.
And time is money.
They learned how they could do more with less effort. How with Microsoft Excel they could expand their capabilities almost overnight. How they could easily add profits, structure their company, and chart their progress.
In a snap.
Word for Windows showed them how to change with the times, communicate clearly and emphatically with their entire organization with a mere click.
I love that.
Now Canterbury Clock Company has more time to build their business. And Joe, well, he got a big hand. Discover why more and more people like you are making the switch. Call now and request your free video, The Switch is On. Call this number now and see for yourself how Microsoft Excel and Word for Windows are changing the face
Yes.
of how business does business.